The PNA here is the heart of the system, and we will be using this system to generate the modulated signal. So some of these capabilities are new. They'll be introduced at the ARFTG conference, in fact. The two brand new capabilities are the internal sources can now be modulated up to 6 gigahertz. So all of these amplifiers are below 6 gigahertz. So we can generate essentially an arbitrary waveform generator file. The file is a little short. The waveform memory is a little short. So we're limited to, at 100 megasymbols per second, we're limited to 600 symbols, but that's plenty for the evaluation we're doing today. So the source one will generate a modulated signal. It will come out the test port. We're going to use an external amplifier in this loop here, as was said before, because we need to boost the signal up to as much as 1 watt to drive some of these amplifiers. And PNA doesn't have that much power. One interesting thing to note, I'm set up on the initial measurement. So I've actually can measure both the input signal and the output signal. This is the input signal going into the amplifier, and we see some distortion in the input signal. I can change the setup to bypass the booster amplifier, so we can see the quality of the signal coming from the source. And if I look at this, it's got a 65 dBc ACPR. So the arbitrary waveform generator inside the source is almost perfect. That's probably just wasteful. But when I switch to go through the booster amplifier at this power level, now we're only generating 44 dBc ACPR. And that's not going to be good enough to test the amplifiers. Fortunately, we have a capability of adding a kind of Dpd Pre-Distortion to the arbitrary waveform generator, where we measure this input signal, pre-distort it to generate a clean signal. And we call that the source modulation cal. And if I turn on the source modulation correction, now you can see that the signal is clean again. And I'm getting around 65 or 66 dBc. At some power levels and some frequencies we can do better, at some we can do worse. So that's when we generate the pre-distorted waveform for testing each student amplifier, we will have to do a distortion correction, and I'll demonstrate that when we do it. Finally, just to start out, before we do anything, we will do a turn on the amplifiers. And the very first thing we'll do with the amplifiers is we will test the S21 gain, and I've set up an S21 gain, and here you can see it's measuring within 0.01 dB, so should be quite reasonable to measure your amplifiers. Hold that channel, and then we will test the amplifiers, each one of them at a power of 21.8 dBm, and make sure they put out 32 dB of power. That's kind of the entry criteria. Finally, after we've done the characterization or first measurements, we will switch. We have the ability do this. We have the ability to use what's called a vector signal analyzer, and this is also another new capability that will be introduced at the ARFTG trade show and RWW trade show, the exhibit. We have the ability to transfer this measured data to the vector signal analyzer, and then we can measure the performance of the input and output. So here, it's a little difficult to see because it's small, but we're seeing 0.17% EVM at the input signal after the correction. That's the equivalent of a minus 55 dBc EVM, if you like EVM and dBc numbers. So we'll do that before pre-distortion, then we'll do it again after pre-distortion, and the difference will be this. Go to number 2, there we go. So just basically I had to adjust the voltage like 10 millivolts, a very small amount. And within 1 milliamp, we'll call that good enough. All right, so switch back to the analyzer if you would, please. Turn the RF power on. Take a sweep. Put the marker at 1.75. So we see this amplifier has a small signal gain, S21 gain of 12.08 dB. Actually, continuously seems pretty stable. All right, now we'll switch to the ACPR measurement. We'll set the input power to 21.8. And we can, this is the input power trace, this is the output power trace, so I'll make that big. And the output power is 33.5 dBm at 21.8, so this amplifier qualifies. So the next step is to now find the point where this amplifier generates the proper signal level. And before I do that, I'm going to save all of these files into individual waveform files. So take the power here. We're going to take the power down to maybe 15 dBm, and we're going to look for something like -40, -38 dBc of ACPR. A little lower than that. I want to get to make sure that we are coming up to the -36 dBm level from the bottom to there, and maybe one more.
And just to let everybody know, we're the upper and lower ACPR, we're taking the worst of the two.
Yeah, we'll be looking at the worst case. So here we are at least 2 dB below the limit. We can see that this upper trace, the input ACPR is 56 dBc, roughly speaking. And so that's 20 dB below our target level, so that should be good enough to not interfere. So now we're going to raise it until we cross the 36 dB level. 37. 3692. 3630. 3620. Oh, 3602. So you notice this ACP is coming up higher. That's pretty close to the 36 level. If I go up one more dB, it will be over, I believe. Right. So for this amplifier, and we're going to try and set the level for ACP 36 plus or minus 0.1 in these settings. So first set of recordings is, this is the output signal. You can see the ACP regions at 16.94 dB input. We have 28.57 dBm output power. So when we do the pre-distortion, this will be the target we try to set. And the current for this level is 83 milliamps. I'll show the current monitor also in there. Okay. You're not updating that.
It seems really slow in updating.
Are you using BenchView or are you using your desktop?
Using the web.
Oh, there it is.
It's really slow.
Just have to wait for the web to update it. All right, so that's the 83. And then just so we know what we have, before I leave this, I'm going to save the screen. Make sure I save it in the right folder. This is the 1.75. And we're going to save this screenshot. We'll call it the RWW. This is the ACPR 36. It's really minus 36, but we don't have to set the minus. This will just record the screen. And that way later, if we have a question about what was something, we have it listed here. All right, next, we go to the Vsa screen. And we started sweeping. And I'll start the equalizer. And I should have reset the equalizer. Oops. Where'd it go? To remove linear frequency response errors, we'll always compare the equalized EVM. Let me reset it, because I wasn't trying to reset it. Okay. We'll watch the EVM numbers. We can see the equalization error coming in. This basically is taking out the
yes, they were very charmed by her. They were like, she's like.
All right. Somebody
accidentally unmuted.
So, all right, so we can see the input has a little bit of error, like 0.05 dB unflatness after the source modulation correction. And we can see the unflatness of the amplifier. It's maybe a dB going from minus 0.75 to 0.75. So across this 100 megahertz bandwidth. And after equalization, we record a value of 1.71 for the amplifier and 0.171 for the source. Right there. Well, actually 0.17. We'll do 2 digits. I think that's probably reasonable. So around 0.17 and 1.71. You guys got those numbers? Okay. And so that we can remember it, I'm going to save the bitmap. We'll call this RWW. This is a VSA measurement, VSA 36. And then finally, this is actually the raw data coming out of the amplifier. This is the IQ waveform that's coming out of the amplifier. We're going to save that trace, the selected trace. I'm going to save that as RWW VSA with a source modulation cal at the 36 level. All right. And this amplifier is done for its 36 dB level. Now we will go to the 33 dB level. So now I'm going to raise the power. We'll go back up to the 21.8 dBm level, and I'll back the power down. Well, we'll see where we are in DVC. Yeah, so here it's 32. I want to go a little higher to make sure it doesn't go back lower again. 31. So we're going to back this until it comes down to minus 33 on a worst case EVM. All right, 1, 2, 3 notches. Still over 32. Okay, just drop below minus 33. It's not quite within 0.1. Okay, that's over the limit, so we're going to back off. That looks like the best we can do with a 0.1 dB resolution on the source power. Slightly lower. So for this amplifier, we're going to record it as, let me make it, that's a little closer. I think I can get 500s increment. Oh, still over a little bit. All right, so now we've dialed in the power, I think. There we go, it's within 0.1. So please record 1884 for the input power and 30.65 for the output power. Set the equalizer. The current is 116.
And what about the gain? The gain of the
gain should be 11.8 dB. For those of you playing along at home, the two digital readouts have the same information. So you can see the carrier input power, the carrier output power, the carrier gain, and the worst case ACPR. And we check the input ACPR is in the 60 dB range, so that's quite good. That's because I've previously done the pre-distortion cal at several different power levels. All right, now the next step is to save this data. Save screen.
Save the screen capture.
It'll be RWW 30, ACPR 30. And your last comment was?
I need to save that.
Thank you. And now we'll switch to the VSA. Previously, I'd started the equalizer, so it looks like we have very, well, we should expect this. The input source is 0.11 EVM, so it's not contributing much. And the EVM of the amplifier is 2.30. 2.30. All right, and we'll save this file. Save. Select a trace. Oh, cancel that. File. Save the bitmap. Save. And this is the RWW VSA 33. That's just a record. We can look back. But what is needed is we have to save the IQ trace. So we say save selected trace, which is the IQ trace, and it will be 33. Okay. Okay. Now this part's a little unhandy, but it's what we have to do. We'll take these two CSAV files, this one and this one. These are the two output, the raw waveforms coming out of the amplifier without distortion. We will copy those. And in this window, this is where our DPD code runs. I will paste them. Now we'll go to the MATLAB code, and this now needs to be RWW, and we have 33 notice. So that's going to read in the waveform. This is the ideal waveform, and we're going to compute the DPD by saying run. And if the internet works and I can get my license, I say running, it should be running. What goes on here? There it goes. I guess first time it must have lost its license overnight, had to go out and get a license. All right. 36. So these are the two power levels. It'll say run again. That should happen much faster. There it goes. All right. We come here and now we have two files, this file and this file. It has the SR. Those are now the DPD waveforms for those two power levels. So we'll put them back into this folder. Now we go back to the VNA and we'll return the power level to the 16.94 dBm level. That was the power level for the minus 36, and it's close. These things will tend to drift around a little bit as the amplifier heats and cools. We'll use that same, in fact, we should be setting this level. So I have to set this 16.91. Because the booster amplifier can drift and actually its compression can change with the modulation, we don't use the power level setting, we use the power level reading. And if we get within 0.05, I'm going to call that good enough. That looks about the right output power level. And we're very close to minus 36, just off a little. Let us now bring in that modulation file. So that's the undistorted waveform. Oh, before we do that, let me save this power trace in memory. Math, data into memory. Data. All right, now, instead of using the original waveform, we're going to load the 36 dBc digital pre-distorted waveform. We see some improvement here, but there's one thing we have to be careful of. The new waveform is actually going into the amplifier, but the booster amplifier from the PNA could be distorting it. So we're going to use this function called source modulation cal to adjust the distortion of this amplifier. Was that
Power count with this step.
can or not? Well, let's see. I think 4 iterations, and we'll look for, again, the minus 56 dB limit next. Calibrate. So what it's looking is to make sure that the normalized mean square error, you could think of it as the error vector magnitude of the entire waveform, is going to be tried to be improved. And the distortion, this is the normalized mean square error, or we call it the distortion EVM, started out at minus 36 dBc, which is not good enough to see your amplifier. But after one iteration, we got to 56. So now that should make the input waveform perfectly represent the demodulation waveform. And now we see a quite improved demodulation. So the secret to getting a good digital pre-distortion is that the waveform you put into the amplifier has to be the proper representation of the pre-distortion model. So now, final step is, because it has a different peak to average ratio, we're going to have to adjust that power level a little bit to get back to the original power level of 28.5. That's within 1/10 of a dB. And so now we can record the new pre-distortion levels. The worst case ACP is -47. File, save screen. We'll call this the RWW ACPR DPD 36. Now we know that. Reset the equalizer. And now we can look at the EVM. It'll take a little bit for this to, I'll have to reset. So I just reset it, and now it's doing the equalization. I'll have to let the equalizer run a little bit. On the 0.6. We'll let it go until the numbers quits changing on the negative lower direction, 0.5.
Bottom left display would be the
What's that? It's this one, right?
raw value on there now.
Sorry.
Oh, just, I was looking at the diagram. On the left, it has the raw value right now showing.
Oh, yes, this is the raw.
There.
This is the actual output constellation. It looks like 0.46 is where it's settled. And let's go ahead and look at the frequency response to the equalizer. It's very good. It's less than 0.1 dB, 0.05 dB per division. So we've now achieved the final level. File, save, save, and we'll call this the RWW Vsa DPD 36, and we recorded that. Now we have to go back and do the same thing at power level 33.
Sorry, Joe.